Flagco is a leading flag producer in the Southeast, making everything from 30-foot flagpoles to little 2-inch toothpick flags. They have a problem, however. Their toothpick flag operation is done completely manually at the moment. This limits throughput and directs employees away from high-value tasks. They needed someone to automate this process. That's where we come in, 6 mechanical engineering students who are ready to tackle the problem of automating toothpick flag manufacturing. When presented with this problem, we created a team called the Toothpick Lovers, and we took on the task of automating the production of these flags to the same level that has been done manually for years. Flagco prides itself on quality, making high-quality bamboo toothpick flags. Each toothpick flag is made of a bamboo toothpick and high-quality cardstock paper. They are 2.75 inches tall and around 1.5 inches wide. With this small of a product, it's challenging to automate this process, but the Toothpick Lovers are up for the challenge. Currently, the process is done completely manually. The operator starts with a flag, a toothpick, and some food-safe glue. The operator first dips the paper in some glue, puts the toothpick in the middle of the paper, and then manually folds the paper together, making sure to compress properly. As you can see, this process is pretty messy and leads to a lot of flags being thrown out due to quality control. Our goal is to automate this process. This is the design that our team came up with. It's a full aluminum 2020 T-slot frame with removable acrylic sides. It has an MDF base for all the electronics and all the subsystems attached straight into the T-slots with T-nuts. Completed flags exit outside the acrylic into an ejection bin. The first subsystem we're looking at is the toothpick dispenser. This is fully custom made with custom mounts both for the device itself as well as a stepper motor used to drive a slotted wheel which dispenses a single toothpick at a time. A problem we faced was toothpick jamming. Therefore, the sloped reservoir only allows one toothpick to escape at a time. This is one of our most successful systems and works with around 90% accuracy. A dispensed toothpick is fed into the slider system with a toothpick channel. This is driven by a pulley on either side connected with a slotted belt. This is all on an 80/20 aluminum frame that is driven by a NEMA 17 motor. We chose this design because of how easy it is to customize it to our specific needs with the adjustability of the 80/20 aluminum and then the use of press fit bearings which allow for low friction and high controllability in the movement of our toothpick. Since toothpicks are so delicate, this is one of our critical systems and a system that we perfected early on in the design process. The paper, on the other hand, is fed using a vacuum pump system. This subsystem definitely gave us the most issues, but we were able to use a custom nozzle paired with a vacuum pump to create suction between a singular sheet of paper and the vacuum. Then, using a NEMA 17 motor, the arm swings around and places the piece of paper into the right place to get ready for fold. After the paper is placed, glue is dispensed. The glue system uses a 500 milliliter reservoir along with a peristaltic pump and custom nozzle mount. This allows glue to be dispensed without touching the paper and changing the friction properties of the paper. The toothpick slider then catches this prepared paper with a toothpick and pulls it through the folding and compression system. This system uses 32 density foam to create a good fold and compression. Lastly, the paper is ejected into an ejection system and bin. So now enough CAD, let's see some live demonstrations. As we can see here, the toothpick is dispensed into the toothpick channel as the slider starts moving down. Then, through the folder, the paper is folded through the series of 32 density foam and eventually ejected. If you didn't see, you can see the glue method dripping glue as the folder comes down. And then for the paper method, you can see the vacuum pump picking up and moving a piece. Along the way, we faced a couple challenges in our design. First, we had a lot of small components. Both the toothpicks and the flags proved to be very delicate, and since we had to operate on such a small scale, we had to have tight tolerances with our manufacturing processes. A challenge with full automation is that it requires you to account for outliers. It requires you to account for the toothpick that's a 1/4 inch larger than the one before it, and a piece of paper that's already torn. This means our design had to be easy to unjam which is why we made some of the design choices we did for accessibility for the operator themselves. Lastly, there was a lack of prior art for this problem, and therefore previous projects were hard to take from as there were just limited information and limited success on these previous projects. Moving on, there was a lot of conclusions we could draw from our work. First, what worked? We were well within the size and weight limits of what was required of us. Also, we exceeded the current production rate as our max production time was 27 seconds. Additionally, we were well under the $900 budget that was allotted to us. Some things that need some improvement are the overall accuracy, as we were only able to obtain about 50% accuracy for our product. Additionally, we would like to reduce the uptime and setup time to make it easier for any operator that uses this. However, we are very proud of our work and we're very excited to see the next steps that the sponsor has in mind.